they're different enough to be considered two different species. All right, so I wanted to start off with some pictures of me and my frogs that I did research on. The one on the left over here is Smilesca bowdeni, and this picture was taken at Palo Verde National Park in Costa Rica. And this is Smilesca manisorum. Can't really see him because he was a jumpy one, but there he is behind my glove, and this was taken at La Selva Biological Station in Costa Rica. So, for some background information, I'm sorry if I go a little quick, but we're on a time limit, so I'm going to try to get through this as fast as possible. So, Smilesca bowdeni and Smilesca manisorum are cryptic species. Cryptic species are two or more species that have a substantial amount of morphological similarity, which means that they look a lot alike, but they represent different species when genetic analysis is performed. Cryptic species can be identified by analysis of their morphometric traits, which is what they look like. One of them, or they're all displayed over here, but the main one is the snout vent length, which is shown right here. It goes from the tip of the nose to this area called the vent. Then they also do take the body mass. That is another very common morphometric trait. Then they can be analyzed by differentiated by analysis of their genetics and analysis of their vocalizations. And that is what my project focused on, the analysis of the vocalizations. For a little bit more background, vocalizations are produced by the contraction of the flanks. So this pushes air from the lungs into the mouth, and as it crosses the vocal cords, it produces sound. Some frogs have vocal sacs, which you can see in this picture. This is a Smilesca bowdeni sample. I'm sorry that it has been euthanized. It's a little tragic, but here's the vocal sacs right here and right here. Some frogs do lack vocal sacs, which just means that their vocalizations tend to have lower frequencies. So there are different types of vocalizations. There are reproductive calls, which are the most commonly heard, and there are specific type of reproductive calls called advertisement calls, which is what a male uses to attract a female, and that is the type of call that I recorded. There are also aggressive and defensive calls, which are used to deter or warn predators, but they are not as likely to be heard. For a little bit more background, when analyzing the vocalizations, you view it in a waveform and a spectrogram view. This top image is the waveform and the bottom is the spectrogram. The waveform is used to look at the temporal properties, and temporal properties are anything that has to do with time. So examples of these would include note and call duration. And then spectral properties are viewed on the spectrogram, and they involve frequencies. So this would be dominant frequencies and fundamental frequencies. Also, there are parts of vocalizations. So this is actually just one call, but it is composed of 3 notes. So that is why you see the 3 different peaks there. And for your reference, I will play the call of Smilesca bowdeni. This is Smilesca bowdeni. And I'll cut that off. And then this is Smilesca manisorum. And that was a chorus of them, so there was multiple calling, but I thought that was the best quality one that I could find. So obviously I think this research is very important, but some key points of the importance are that this will allow other researchers to differentiate between these frogs in areas of overlap using only vocalizations and not genetic analysis. Vocal analysis is preferred over genetic analysis because it is much cheaper. The equipment used for genetic analysis is very expensive, and genetic analysis is also very time consuming. So for my project, we are conducting genetic analysis, and we collected the samples last May, and we still don't have the results, so it can take quite a while to get the results back from genetic analysis. Also, when recording the calls of individuals, it does not harm them. When taking genetic samples, sometimes you do have to euthanize them in order to get a voucher specimen and in order to make sure that you have enough DNA for the genetic analysis. So this can sometimes be very tricky when you're studying endangered species, because if voucher specimens are being taken by several different researchers, this can have an impact on a population of individuals that was already pretty low. Information can also be gathered about the distribution, conservation status, and the behavior of each of these cryptic species, which can be important for further research. So this is what we do know and what we knew before I conducted my research. So Smilesca baudini and Smilesca manisorum were recently separated in 2017 based on morphology alone by McCraney. They were separated based on adult size, and that manisorum had a consistently larger adult size, by the presence or lack of webbing on the hind limbs, in that manisorum had more webbing, and the shape of the inner metatarsal tubercle. Manisorum's tubercle is longer and flatter, and I will show you a picture of that in a few slides. Also, the advertisement call of baudini was described in literature by Duellman as having a note duration of 0.09 to 0.13 seconds, 2 to 15 notes in the call, which can seem like a pretty large range, but I have observed in my research that it's typically on the higher end of the scale when frogs are chorusing with each other, so when there's more than one calling and they're calling in response to the other, and it's on the lower end of the scale from 2 to 4 when it's just one individual calling at a time. Notes also have 140 to 195 pulses per second, and the dominant frequency of 175 to 495 hertz, which is the fundamental frequency, and that's why there's two. Then the higher end is 2400 to 2725, which is the overall dominant frequency. So the goals of our project were to record and analyze the calls of Smilesca baudini and Smilesca manisorum and use these analyses to verify that the assumptions that McCraney made are valid and that Smilesca manisorum and Smilesca baudini are actually distinct species. We collected tissue samples and are still in the process of analyzing the genetics of the two species, and we also took morphometric measurements and we compared them. So this next slide is our materials. We have the Kestrel 3000 right here, which is the weather meter that we use to take different weather parameters. We also have the Audio-Technica ATR 6550, which is the shotgun microphone. It's important to use a shotgun microphone because it only records in a cone shape. So if I have the microphone pointing in front of me, I won't record what's happening behind me, which is really important to block out background noise. Because as you can imagine, in the rainforest in Costa Rica, there are so many frogs calling. So if you just want to record one specific frog, it's very important to use a shotgun microphone. We paired that with the Tascam DR05 audio recorder over here, the red. And then we used a Pessoa spring scale right here to weigh the frogs. And we paired that with a Ziploc bag. We will put the frog in the Ziploc bag because you can't really just clip it onto the frog. So we would put the frog in a Ziploc bag, weigh the Ziploc, and then take the frog out of it. And the Ziploc metric measurements of the frog, such as snout vent length, and we use Raven Pro software to analyze the data. Did you lose me? I feel like, did I cut out a little bit? Am I good? I'm here. Okay, sorry, my Wi-Fi is a little bit spotty. So when we were actually conducting our research, we had 5 different study sites in Costa Rica where we located the frog of interest by walking along trails, and we would listen until the expected vocalization was heard. We would record weather data on the Kestrel 3000. As I mentioned, these parameters included air temperature, relative humidity, and wind speed, and we made sure to record these because they can affect the variables of the call. Once we heard a call, we would get within 1 meter of the frog if we could, and we'd record it under red light of our headlamps to make sure that we didn't disturb its natural calling pattern, because white light can do that. Then throughout the recording, we would visually confirm that the frog was still calling and that we were recording the right frog. And we would record at least 10 calls from each individual frog. If we could get more, that was great, but at least 10, while taking note of its calling behaviors and its position. Then we would make sure to capture the frog after recording it so we didn't disturb it. We would take the morphometric measurements, such as snout vent length, as I showed you before, and the weight of the frogs. Here is a picture of us taking the snout vent length of this little frog. This is not a frog I used in my research, but it's a great picture. Thank you, Prof. Twining, for taking this picture. And the picture at the top, too. And this is my research partner, Carly. After we took the morphometric measurements, we would obtain genetic samples. First, we would swab the frog, aggressively swabbing the skin with a Q-tip looking swab for about 20 seconds until we felt like we got some DNA. We would break it off and put it in a container with ethanol to preserve the sample. We would also take a small piece of its toe, its little toe pad, slice that with a scalpel and put that in a container to have some more genetic samples. And if we had one voucher specimen that we did keep, we euthanized it and submitted it to a university for preservation. And this was the Smilowski bowdeni individual with the highest quality recording. And we took a liver sample from that individual for genetic sampling. So after we did all of this, we downloaded 68 photos of the metatarsal tubercles of either Smilowski manisorum or bowdeni, and they were put into a spreadsheet and scored as a 1 if they were low, long, and flat, as a 2 if they were moderately raised, which we tried not to score it as a 2 because that doesn't really give us any explanation on what it is, and then we would score it as a 3 if it was short, raised, and globular. For our data analysis, we would make selections using Raven Pro software. First, I would select this. So this is one call with 3 notes in it. I would select this on the spectrogram, the whole call, and I would make sure to start at the top and end at the bottom. And then I would select just the fundamental frequency at the bottom of the whole call. And then I would select each individual note on the waveform because it's a lot easier to see the distinct beginning and end on the waveform than it is on the spectrogram. So I would make sure to select it up here to have more accurate results. This will put everything into a chart at the bottom of the page, and then I organize that data into a spreadsheet, and I shared that with my research partner. To analyze the data that we obtained, we compared all the properties using a t-test with a 95% confidence interval. So here's some of my results. This is a waveform and spectrogram view of a call from Smilowski bowdeni on the left and a call from Smilowski manisorum on the right. The top is the waveform view and the bottom is the spectrogram view. This is one call consisting of 5 notes and also one call consisting of 5 notes. This is just for a visual comparison. It doesn't really tell us anything about the parameters, but this is just to look at it, and you can see that they do look similar, so that's why we need to analyze them using an actual software. Here are the results from the tubercle assessment. So you've heard me talking about the tubercle, but you probably don't know what it looks like. So here it is, this little tiny blob circled here. This is the tubercle for bowdeni. It is much more raised and globular and prominent than the tubercle for manisorum, which is down here, which is a lot smaller, flatter, and longer. And then this is a bowdeni individual. This is a manisorum individual. And our results confirmed that McCraney's assumptions were correct and that this is bowdeni and this is manisorum. So here's the results from bowdeni of 5 individual recordings. This is a lot of information, and it's more just to show you the means, but I'll summarize the information on 2 slides. So these 2 recordings at the bottom were from the Macaulay Library, which is an online database where you can get recordings to increase the amount of data that you have just to make your results more accurate. So that is where these 2 are from. And these are the temporal parameters here and the spectral parameters here. As you can see, these have to do with time and these have to do with frequencies. And here is the similar thing for Smilowski manisorum. This is 8 individuals and we have 34 more. So I picked the 8 that had the best quality, I guess. As you can tell, I couldn't include 34 more on this slide because that would look a little cluttered and not very good. So if you really want to know, you can let me know. But this is the means for 8 of all of the individuals. So again, temporal parameters, spectral parameters. And now on to a more understandable summary. Here's a comparison. So we did confirm Dwellman, how he explained the Smilowski bowdeni, 1 to 15 notes, quickly repeated 1 to 15 times with a mean of 4.07, a mean note duration of 0.1 second. and a mean dominant frequency of 2,440 hertz. And the numbers with the plus or minus is the standard deviation. Also for Manisorum, it sounds similar to Bowdeny and is repeated 1 to 20 times with a mean of 6.82, a mean note duration of 0.12, and a mean dominant frequency of 1,434. And also the standard deviations are included. And since Manisorum has never been described in literature, we do not have a baseline to compare it to, but that was one of the goals in this research. So for our discussion, the two species had the same mean note durations of about 1.11 seconds. The significant differences were in the number of notes in the call duration, rate of notes in call, duration 90%, and dominant frequency. So you can tell if they're significant if the p-value is less than 0.05. And that is the p-values of these. All right, finally, for future work, I'll have to rearrange my data in the spreadsheet that I share with my teammate as the individual frog unit, and I will analyze more calls and perform a statistical analysis on that, and I will work with my team on writing a research paper for publication. All right, that's it. My acknowledgements. I thank John Twining from ENC, John Cassell and Carly from NNU, and all these other people for their contribution of audio files. Thank you.
Thank you, Liz.
Yes.
I know it comes to sort of an abrupt ending because it's like they can't really applaud, but let's assume that the audience is applauding at home for you.
I will assume. Also, I posted this, so if anyone wants to go back and see it.
Yes, the slides are available on the Symposium Canvas site, so certainly you can revisit them there. Liz, I don't know if you saw. Did you see Professor Twining's question?
I have not yet, but I do
asking,
now.
Yeah, why is it that you can use vocalizations to differentiate between two species, and what is the reason for that? Yeah. And then I would like to add a question of my own, which is not exactly related, but are the differences that we're talking about here actually perceptible to the human ear? In other words, if I had these two frogs in my hand, or if they were hidden in the woods behind, would I be able to identify them using only my ears, or is this a determination that has to be made with the kinds of equipment that you describe?
All right, those are both great questions. I appreciate the questions. I'll answer Professor Twining's first. So you can use vocalizations to differentiate between species because they are heritable and they are unique to each species. So each species will have a unique vocalization. So this species will have a much different vocalization than another species. So that is why you can use vocalizations to differentiate between the two species. To answer Prof. McCoy's question, I do not believe that you can differentiate these two just based on listening. I played the vocalizations in one of my slides, and it's really hard for me to tell the difference. Even when I was in Costa Rica, I was like, okay, I think this is this one, I think this is this one. So it's definitely important to use a software that actually can see the real numbers rather than just relying on your ear to tell the difference.
Okay.
I know that Prof. Twining just made a note that Manisorum is definitely lower. You can hear that. So like if you would play them right next to each other, you could probably hear that. Yeah. But if you just hear one without reference, then I think it's very hard to tell the difference.
In the chat, Tara Brooke Watkins asked you about why were these two frogs originally seen as different species? And what does it mean in kind of the big picture? Like, what is the significance of knowing in the context of environmental studies that they are in fact different?
Yeah, that is a great question. Originally, it was just recently in 2017 that McCraney did separate the two species based on simply how they looked, based on the adult size, the presence or lack of webbing, and the metatarsal tubercle, which is a mouthful to say, but it was in the picture that I showed. So that's how they were separated. So that's why this research was important, to separate them based on more than just how they looked, based on genetics and vocalizations as well. And it's important to know if there's two species or one species, specifically for like conservation status, and knowing how many of the species we have and how to improve their numbers, I guess is how I would answer that question.
Thank you, Liz.
Yes, of course.
Greatly appreciate it.
No problem.
We're going to go ahead and move to Jose's presentation. For those of you who are still out in the audience, I did want to say that if you do have additional questions, oh, and I see, Liz, that Professor Waterman has just asked you a question. You can still submit those questions really at any time. And Liz can either type responses to you directly, or we may, if we have some additional time at the very end, we may simply sort of throw things open for additional questions. But Liz, if you want to answer Professor Waterman there in the chat or in the Q&A box, I'm sure that he would appreciate that.
All right.
All right. Well, thank you, Liz.
Thank you all.
And Jose, the floor is yours. Liz, can you get your slides down, or there should be a stop sharing button. Got it. All right.
Perfect. Okay. So if at any point in the presentation, Prof. McCoy, there's issues with the audio with the slides, just let me know. Okay. Thanks everyone for being here. My name is Jose Amilcar Mata, and tonight I'm glad to present to you guys my senior design project titled The Plant Growth Station: Aiding the Average Person in Becoming a Better Gardener. Okay. So basically the problem that we're trying to tackle and the nature of these projects is that we're taking a problem of the real world and we're trying to develop a product or find a solution to it. So the problem that I'm trying to tackle with my project is that basically the average person doesn't have real gardening experience. So the regular person won't have any experience growing plants, especially if they're a special type of plant that has very specific conditions in which it grows better. Because some plants have temperature ranges, have humidity ranges, and light level ranges in which they grow better. But even if you know these conditions, it's difficult to make sure that your plant is under these conditions at all times, especially if you're new to this hobby. So the plant growth station addresses the problem by letting users know the temperature, the air humidity, and the light level of the plant, and it does this online, so the users can look at the values pretty much in real time. From wherever they are. And there's also some email services that are going to help the user stay on top of these values, which I'm going to get into in a second. So summarize, we can say that the main purpose of the plant growth station, which I also call the PGS, by the way, is to aid customers in the process of growing their own plants by providing a way to monitor the plant's conditions online. So the customers that I expect for the product is pretty much everyone from a young adult demographic to elders or anyone really who is interested in growing plants. And the good thing is that you don't need to have any sort of experience in it. So you don't need to really know how to do anything. The way the product works, you just turn it on and you're pretty much all set. So the system requirements are the things that I wanted to make sure that my product have from the very start. So the first one is to provide a container in which the user can grow a plant. So you just buy the product and you're pretty much ready to go. The second one is that the product itself can be powered from an outlet with the standard 120 volts and 60 hertz frequency. So you just plug it in, turn it on, and that's all you need. The third one is one of the services itself, which, as I said before, is displaying the temperature, humidity, and light level values measured online. So if you access the values online, you're going to be able to see them in a graph format, so you can see how they've changed through time. And the email services to help the user stay on top of these things. So there's two different types of email services. The first one is the email alert system, and the way this system works is that you go online, you set your values for each of the sensors. So you give it a temperature range, a humidity range, and a light level range. And if your values ever go above or below that, then you're going to get an email that warns you of that, and it tells you what the current values are. And the second email service is email report, which is basically a service that makes it so that every day at 8 p.m. you're going to get an email to on your inbox that's going to tell you the average of each of these sensor values for the past 24 hours. So you have a better idea of what kind of conditions your plant has been exposed to. So this is the overall product architecture. Here, there is a 3D design of the rough structure of it. There's the container. These two are the sensors. And here's the Raspberry Pi, which is basically a small computer where the data is gathered and processed. So the sensor data from the Pi and whatever input the user has through the website is sent to the web application, which is where everything is programmed and all the data is processed. That is stored in two different databases, and from the databases you can see the values, as I said before, in graphs, so you can look at them as they are being received. So this is the device itself. This is the container, and this little black box in here is the Raspberry Pi, the little computer, as I said before. The only thing that you need for it is to be plugged in, and there's also an Ethernet cable that's connected to it, so it's connected to the internet. Here are two different views. As I said, this is the Raspberry Pi, and these are the two sensors that are used for the system. This is a complete setup. On one of the screens, you can see the website, which I'm going to talk about, and the graphs. So the total cost is about $114. These are the cost of the materials that it takes to make this. But of course, there's these may vary depending on what exactly you get. So for example, the plexiglass container, depending on the size you want, you can get different prices. So how it was built. As I said, the Raspberry Pi, if you've never heard of one, what it basically is just a small computer and a single board. It's very powerful, and it has all these specifications that you see on the screen, like Wi-Fi, Ethernet, and the input-output pins that I'm using. The temperature and humidity sensor that I'm using is very accurate. It measures temperatures from -40 to 80 degrees Celsius and humidity from 0 to 100%. And it has an accuracy of 0.5 degrees Celsius and 1% humidity. The light level sensor is this one, and it measures light in units of lux. It goes from 0 to over 65K lux. So in order to develop the software part of this, I use the ENC Linux server. So I deploy my application on one of the ENC servers. Flask is the name of the framework that I'm using, and Python 3 is the name of the language that I use to code, which is a high-level language. Cron jobs to program specific tasks to happen at specific times. The SQL database, which is a relational database where I'm storing the user information, like your email, your username, that kind of stuff when the user signs up on the website. The Influx database, which is where all the data from the sensors go. Grafana, which is what I'm using to display the graphs. And GitHub, which is basically just a cloud where I'm storing the entire application. So the plant growth station has a website, as I said before, and here's a video demonstration of it.
Hey everyone. Okay, so this is a demonstration video in which I'm gonna show how the website of the plant growth station works. I'm gonna go through the different features of it, click around the website, show the different pages that there are, and the things that a user can do with it. So first off, this is the home page. You can access it using the IP address of the ENC server that I have deployed the application in. This button over here, it brings you to home, as well as this one over here. This is the About page. If I click on it, then there's a little message that kind of explains what the plant growth station is about and the things that a user can do with it. We go back to the home page here, and then here's the sidebar with the different features. So with the latest posts, it also brings you back to the home page, but it shows the posts when there are any. With the check sensors, this button is going to open another tab, another window, and there you will be able to see the graphs of your sensor values, so your temperature, your light level, and your humidity values. This set email alerts values is going to take you to another page in which you can set your threshold values for your email service. And then we also got the login and the register options over here. So the first thing that a user must do once they log in is to register. So I click on the register option and there's a form that you need to fill out. So I'm going to fill this out for myself. This email that I'm registering with is going to be the email that's going to be receiving all the alerts from the emails and the daily report. So the identifier is the number that is specific to the Raspberry Pi that I'm using right now. So then I sign up with it, and my account has been created. So I have the option to log in here, or I can just click the option over here to log in again. And there, I am logged in right now, and in my account I can do several things. One of the first things that I can do is to create a post. So if I go here and I create a post, I assign a title to it and the content of the actual post. And there we go. Now, when we go back to the home page and we go to latest posts, there it is. And it shows the date in which I made the post. It shows my profile picture and my username. Also in the website, once you're logged in, you can click on your account option that you get up here. And here you can see your profile picture, you can see your username, you can see your email, and you can change several things. You can change your username, email, and your profile picture. If I were to want to change mine, but this is the default one, for now I'm going to leave it like that. And then you can also see your PGS identifier that you registered with. Once a user is logged in, they can also click this option here, set email alert values, and this brings you to this page, which is basically where you're going to set your maximum temperature, humidity, and light level, and your minimum temperature, humidity, and light level. So if your values go above any of these values that you set here, you're going to receive an email alert. Or if they go below the ones you set here, you're going to get one too. So the default values are already set to be very high and very low. So it's as if you did not have the alerts activated. But I'm going to change mine. I'm going to make it so if it goes above 26 degrees Celsius, I'll get an alert. If it goes over 70% of humidity, I'll get an alert. And if it goes over 1000 lux, I'll get an alert. I'll leave the other values as they are for now. Submit them, and we're all set. Finally, you can also check your sensor values in the graphs. So if you click this button here, which says check sensors, let's open that in a new tab. Then you're going to come to this page, and I've already set the dashboard. So then these are the sensor values. Right now, they're set to display the last 3 hours of data. So I was checking some data just recently, which is displayed right here. You could also set it to whatever you would like to have. So the last 15 minutes, and you have it set for whatever time that you want it to update. I have it updated every 5 seconds so that it's as real time as possible. Finally, here's another example of what the website may end up looking like if it had more users in it. This one has 4 users created, and each of them made a post, as you can see. If there are more posts or more users with more posts in general, we could browse them using the numbers down here. But for now, these are the posts that we have, and it's just an example of what it may look like once the PGS has more users integrated in the website.
Okay, so one of the other things that you can do is reset your password. So you do that by using this screen. You write your email and you reset it. You're going to get an email like this. And one of the nice things is that the password is actually encrypted for extra security. Now here's a demonstration video of what the device actually looks like and how it works.
Okay, so this is the actual station itself. All it needs to be turned on is this switch over here. Gonna flip it on. That's pretty much it. It takes a few seconds for it to actually start recording the data. So this is the Raspberry Pi. This over here is the power cable. And this is the Ethernet cord. It needs it in order to be connected to the internet and send the values over to the ENC server. And over here, the two sensors. So this is the light and the light level sensor. It has the little orange square in there is the one that receives the light, and the other one is the temperature and humidity sensor. Over here we have the website running. Those are the values that we set before. And over here we have the graph. So whenever the sensor values start coming, they're gonna start displaying, and they just did. So the values that are being sent right now, pretty much live from the Raspberry Pi, are the ones being represented in the graph. You see the temperature is somewhere around 20 degrees Celsius in this room. The humidity is about 30%, and the light level is around 157 lux.
Okay, one of the other videos that I have to present is about the email alert system.
Okay, so for the email alert system, we're going to see now a demonstration of the light sensor alerts. So we're going to turn on this flashlight right above the light sensor over there, which increases the amount of light that it's receiving. It's seen here in the graph that it immediately spikes to 1,200 lux. And if we go to the inbox, we can see I just got an email from Plant Growth Station. If I check it, it says that the plant may be at an undesirable light level. It gives me the level that it's at and the values that I previously placed.
Okay, so that was the email alert service. The other email alert, the other email service that I was talking about is the daily email report, and it kind of looks like this. Only difference is you're gonna get it at 8 p.m. every night. So to conclude, the plant growth station is fully functional. It allows its users to monitor the conditions that their plants are under in near real time. It includes user account creation and personalization. So the aim of this is to kind of create a community of people that are trying to grow plants, that they're trying to share their experiences with others that are doing the same thing. And it allows for personalized email alerts as well. There are future improvements. So if I decide to deploy the application in a service like Google Cloud or Amazon Web Services, then it could work with Wi-Fi instead of an Ethernet cable. And there can also be a database of plants added. So say if you go to the website, there's a list of plants that you can look, and then the website itself tells you what's the best condition for them, and it automates the alert values for you. So acknowledgement first to God, of course. Dr. Pierre Richard Cornely for helping us, me and my classmates, throughout the entire procedure with the systems engineering approach and with his guidance, and with to my family and friends that supported me throughout it as well. These are my references. And if anybody has any questions, I'm more than happy to answer them.
Thanks, Jose. That's really quite a fascinating project. Jose, should I be assuming that you are yourself a gardener? Is this a personal passion of yours?
Ironically enough, it isn't. I haven't actually. I don't think I've grown a plant since I was in like kindergarten. But I just really like the idea of the project when it came to mind, so that's why I decided to do it.
All right, great. And do you imagine? I mean, would it be your aspiration to commercialize this entity? Like, would you hope to sell the design to a manufacturing company? Would you hope to? I mean, are you patenting this idea? What are your future plans for it?
As of now, like the patent is generally what we talk most about in class. In order to get it patented first, I would assume I would need to work on the future improvements that I mentioned before in order to make it like a little more compact so that it can be mass produced. There's some aspects of it that are set up for that. So the identifier kind of that I showed before, it's unique for every Raspberry Pi, kind of like setting it up. So if more units of it were produced, they're already like able to have their own identification number. So users, you know, are identified as their own user. But definitely, yeah, it's definitely in my mind. Like I do want to keep working on the project as a whole, improve it a little more, and then we'll see where that goes.
I would imagine that one of the things that would need to go along with it, and I don't know if you would integrate this into the existing platform, if you would simply direct people to other resources, would be to give gardeners, you know, some clear guidelines for trying to understand like what constitutes the healthy environment for their particular plants and the things that they're trying to achieve. Because I'm a very amateur gardener, and I was listening and I was realizing, oh, I don't know what the ideal, you know, atmospheric humidity is for tomatoes or something of that nature.
Yeah, so I think I included that in the future improvements thing as being implemented in the website in the way like in the form of a database. So the idea is that, you know, users can kind of register the same way that I showed you can so far, but then there would be a search bar or some other option where you can look up the name of your plant or the species, and it will show you the ideal conditions. And once you say that under this certain account you're growing this certain type of plant, then it shows you the information of what the ideal conditions would be, and it also will set the threshold values for the alert. So say if I'm growing orchids, and I think those generally require if I'm not mistaken, those generally require a little lower temperature level than other plants. So it would automatically set those alerts on the email alert system, so you wouldn't have to worry about it, and then you would get your emails if it gets hotter than that or colder than what it should be. But yeah, it's definitely one of the important ideas.
Yeah, great. Well, Jose, thank you. For those who are in the audience, Jose does also have a contribution in the poster session where you can look through his presentation and his paper and the sort of summary of his plans and findings. So encourage everyone to go and check that out. You can leave other questions for him. If they come to you tomorrow, you can leave questions for him there. If you go to the Academic Symposium homepage and click on modules, that'll take you to the discussion boards where you can ask Jose your other questions. But now I think we'll give the floor to Dylan. So Dylan.
All right. Welcome everybody to tonight's main event. I'm kidding, obviously. I will just be wrapping up tonight's presentations with my own team project. So without further ado, once this gets loaded, my name is obviously Dylan LeBeau. I am a candidate for Bachelor of Science in Electrical Engineering. My project, my senior design, is the mobile triple axis fluxgate magnetometer. So let's just jump right into it. Obviously, since Earth's inception, earthquakes have been a very prevalent disaster that have plagued man. So we have fought to try to explain the nature of them and forecast them. Recently, the 2010 Haitian earthquake affected approximately 3 million people, and about 250,000 were left dead. This sparked a nearly decade-long crusade on trying to forecast, earthquakes here at Eastern Iowa College due to our Haitian relation, I like to call it. There are a few other designs in place to try, and they're actually called early detection systems. They can be used as alarms. They don't really give humans a good enough reaction time and still leave, obviously, even developed countries like Japan, which had a major earthquake in 2011 with significant damage. So a small abstract of my design was to design a mobile magnetometer to measure magnetic anomalies that precede an earthquake as something called precursors. I'll touch on what exactly a precursor is in a minute, but in doing that, I designed a user interface that allows people to, in real time, examine magnetic fields in 3 directions for personal use. Also, I aim to contribute the data collected to a network of precursor sensors, which we here have developed at Eastern Nazarene College. Like I said, there are a few other early detection systems in place. You can see the photo on the right is actually a map of the earthquake sensor density in both California and Japan. And you can see there are obviously thousands of sensors in each of those locations, and they are still riddled with earthquakes every year, and there's not much we can do to defend against them. The ones in California specifically are run by the U.S. Geological Service, and they just attempt to use seismophones to determine that a quake has happened. And unfortunately, it gives people in the area minutes at most to respond or get to higher ground in case of Japan for tsunamis. And it's just not good enough. So we aim to continue that. And like I said, even Japan, a very, very modern country, was devastated in 2011. This is actually a photo of devastation. There are about 20,000 earthquakes a year on average. If we could just, take 5 or 10 major ones and give people about a week's notice, I think they'd be pretty happy about it. So, like I said, I would explain precursors. Here at Eastern Nazarene College, we've actually been researching something along the lines of electrical precursors. So electrical signals that exist in the Earth's crust and atmosphere that would give a heads up to people that an earthquake is looming. And my work specifically tied to magnetic anomalies formed from the Earth's crust. What you can see here on the right is actually the original ENC research team. And I'm not positive, but I do believe the man standing right in the middle, right there, Billy Malice, is in the crowd tonight. So we have a bit of a celebrity among us. He actually was a senior as I was a freshman and helped inspire me to work on a project such as this. Moving along towards my system requirements of my magnetometer, the system shall be able to record geomagnetic field data, obviously, and I personally aim to make that in real time because I wanted people to be able to see what was happening around them in real time. The system shall be able to detect 10 nanotesla magnitude changes in magnetic fields, which is the size and the precision of the magnetic anomalies we are looking for. And the system shall be able to compile that data to be extracted for online access. So one of the biggest hurdles of magnetometry is the price. We can see here on the right, or the left, I'm sorry, a online marketplace set for a triple axis flux gate magnetometer that can range anywhere from $700 to $6,000. And in most cases, that is just not negotiable for research purposes. So on the right, you can see the cost breakdown of my device lies at right around $170. Now, my total cost for making that, Ms. Cheryl Burt, I think you're still listening, it was a little bit higher due to some mess ups on my part, but the actual cost for all the components on board is only $170, and I really doubt it climb over 200. So that is a major, major plus for my design. As I mentioned in the previous slide, fluxgate magnetometers, they are a class of magnetometers which measure magnetic fields in direction and magnitude as vectors. Some of those who have taken higher math might understand that, but the fluxgate magnetometer is made up of 3 major parts. You can see in the, let me get on my pointer, bottom right, a cross-sectional diagram of which there is a oval-shaped ferromagnetic core made up of usually iron or nickel, a drive winding, which is a metal coil wrapped around that ferromagnetic core, and then wrapped around all of it, something called a sense winding, wrapped around all 3 of the other 2 components. And what happens is, as the drive winding feeds the ferromagnetic core with an alternating current, we actually drive the ferromagnetic core into saturation of magnetic flux. And you can see points A and D on the hysteresis curve right here. This is what this is called for those of you who are new to any of my presentations. Those are the operating regions in which just normal magnetic behavior is occurring. And as the sense windings, they are there to pick up outside magnetic fields. What happens is they push those saturation regions A and D further and further apart and creates a larger gap between points C and F right here in the coercivity section. And that's how we actually measure the changes in magnetic field. And the challenge is to be able to pick up those small magnetic changes. Now, all of the software besides the hardware and the magnetometers and the Raspberry Pi, everything on board was done with Python. I aim to do that as Python is one of the fastest growing Python or programming languages. And I thought it would help with furthering the technology as it grew outside of my hands. Ooh, that's a little too fast. This right here is a system architecture of my design. We can see that the Raspberry Pi, or the triple axis magnetometer, is made up of 4 major parts. Up top, we can see the Raspberry Pi and something called the LSM303, which is actually what holds the magnetometers on board, and we'll touch on that in just a second. But the Raspberry Pi is responsible for real-time data logging and transfer, as well as acting as a brain to the rest of the system. Here at 3 o'clock on the diagram, we have something called the housing design, which is a 3D printed case, which was designed and printed here at Eastern Nazarene College. It allows for a nice ergonomic handheld feeling and a nice airflow design to keep components cool. The power systems, which are variably the backbone of the project, include a Adafruit power breakout chip, 4000 mAh lithium-ion battery, and approximately a 3-hour battery life. And then the most difficult to implement of all of the parts was the user interface. This is responsible for the real-time display of the data, as well as the options for the user to analyze in 3 different directions the path of magnetic fields that are occurring around them. This was all done in tkinter and matplotlib libraries of the Python programming language. For an in-depth look at the Raspberry Pi, I know Jose just touched on the Raspberry Pi itself and how powerful it is, but in very specific terms to my project, the Raspberry Pi acts as the brain of the system. It allows for the manipulation of data from the sensors. It helps create the user interface. It's responsible for all number crunching. And most importantly, it serves as a power distribution unit. All power from the battery goes to the Raspberry Pi and then is distributed to other subsystems such as the LSM303, the touchscreen, and others I can't think about right now, and maybe a fan here and there, but is obviously incredibly important. And then moving along, the LSM303 triple aggregate fluxgate magnetometer. This is a chip from Adafruit, which encases 3 microscopic fluxgate magnetometers right here. And it actually allows for the capture of magnetic fields with the hysteresis effect and how I explained a little bit earlier. While not expensive, it can be manipulated to be a lot more powerful than it actually is. Like I said, I used Python to program everything, all the software. I used the Thani IDE, pretty straightforward. Just get right past that. And retouching on the GUI, the graphic user interface. The GUI is a acronym for that. Application was using Python's tkinter and matplotlib libraries, as well as some other basic libraries. But it also using Sebastian Arboleda, who is a electrical engineering student, colleague of mine, uses his publisher files, uses his publish application to get our data packaged at 1-minute intervals for display on Eastern Nazarene College's server, which would be our data fusion platform, but that is not up and running yet. But the data is packaged and basically sent to an empty mailbox at all times, even when it's not recording. Here we can see the internal layout of the actual design itself. We have all the major pieces right there. This would be the Raspberry Pi, the lithium-ion battery, the magnetometer itself, or all 3 of the magnetometers, and the power breakout chip. And this up here is the 3D, or the touchscreen display. I'm sorry, not 3D. And it's all comfortably housed within the 3D case, which you can see very nicely here. This be a front view and the side view of the final product or prototype. Excuse me. This is a screenshot of the GUI in real time. Actually, not real time. This is actually was recording in real time, but a screenshot of it. You can see on the right 3 colored options for a user to decide if they want a horizontal, vertical, or full magnetic field. You can select 1, 3, none, It's really up to the user, but they will display them on the graph right in front of you for your viewing pleasure. And then obviously with a device such as this, the only really true way to determine if it works is through testing. So on the right, you can see an image of my testing environment, or my lab testing environment per se, in which I used a signal generator and a DC power source in series with a ton of resistance, which is needed to create a very, very small current, to create very, very small magnetic fields. And if you are not familiar with what this is right here, this is called a solenoid. And if you know the current going through that solenoid, as well as something called a turn density, which is how many rounds of coil and how long the coil or the solenoid is, you can calculate the magnetic field theoretically. And by doing that, I was able to approximately create small magnetic fields for the magnetometer, which in this case was placed inside of the solenoid for most accuracy to pick up. So, and in order to show my data is legitimate, not just some random noise that I was picking up off the sidewalk, we designed a unique magnetic field, an oscillating magnetic field, by producing an AC sine wave through that solenoid. And obviously, as you can see here on the right, the graph shows a very sinusoidal, though noisy because I was in a very noisy environment, but a very sinusoidal magnetic field. So I was actually able to show the data is truly what my magnetometer is seeing. The next hurdle I aimed to jump over was the fact that how would my magnetometer stand up to a largely funded magnetometer? So we found data from a state-funded magnetometer in Ottawa, Canada. Now that may seem far away now, but in reality, the geographics of it really won't change the magnetic field data except for some small local weather patterns, which we can see that by the end of my test, there were some small differences in the data. But on a sunny July afternoon, I was able to pick up the exact same trends as a very, very funded and well-kept magnetometer besides a local weather pattern. I would call that a success, and I am very proud of that test. It was actually a sight for sore eyes how that was going. And then finally, a precision testing, which we had to aim to show that we could pick up magnetic fields in the 10 nanotesla range, which is incredibly small. And what I did was, using that solenoid setup, and I was able to create about 10 to 20 nanotesla pulses, one at about 30 seconds here. You can see the nice plateau, and then it would shut off, and then 3 10-second pulses following that to show more unique fields per se. And I was able to see those 10 nanotesla changes, which was very, very encouraging for my research. Encouraged by Dr. Cornley to do a field test, I was driven to place my device, which you can see right here in the corner of the photo, along a road, and drive a car in front of it twice. We expected to see two very twin identical peaks, or magnetic signatures, I like to call them. And I actually have a demonstration video of this, and I hope this works audio-wise. So what we're going to be doing is controlling the Raspberry Pi magnetometer right there. We're going to have a car right there. Right by it, we're going to see if we can contract the magnetic signature of the vehicle. So here we go. Dr. McCoy, could you tell me if the audio on that video is working?
Yes, Dylan, you were fine.
Okay.
Yep.
There we go. We can see the application running. We're waving on my assistant. She's going to drive by. And she's going to stop and come back. And we'll tell her, whoa, look at that spike. And then we go back down.
Beautiful.
Okay, so the results from that field test right there are shown on the right. You can see here and here two very similar magnetic signatures, which within one microtesla of each other was also incredibly encouraging to see that my device could work in the field full of magnetic disturbances and that it is field ready. In conclusion, I was hopeful to demonstrate to you, as I demonstrated to myself, that the magnetometer was functional, comparable, precise, and most importantly, I have it in green for a reason, demonstrated value compared to other magnetometers of its kind. Obviously, I would like to continue the work on this project. I would like to improve some very cosmetic things such as battery life and a few more features like onboard anomaly detection instead of relying on our data fusion platform, which would take a lot of precursors, not just one, such as magnetic anomalies, and try to develop a danger setting, like a weather report, basically, for earthquakes. And I would like to improve noise filtering, as the Raspberry Pi does create a lot, and I did get rid of most of it, but I would like to improve that. I would like to thank a couple people. Very firstly, Dr. Cornley. He has been on my case since I walked in the door as a freshman at Eastern Nazarene College. And then Dr. Hammerstrom and Dr. Marcus Fries for being both incredible teachers in the mathematics department, as well as very good friends of mine and sources of encouragement the entire time. So yeah, does anyone have any questions?
Thanks, Dylan. This is a tremendous project. If anybody does have questions, please feel free to submit them, or even to raise your hand, and we can unmute you so that you can talk to Dylan directly. Dylan, I did have a question, and it relates. If you want to go back before you stop sharing, actually, if you want to go back to slide 21, where you were showing us your comparable data in terms of testing with the Ottawa magnetometer. And you said that, I mean, obviously you can see the trend until the end there where they diverge.
Yes.
And you said that this was a result of local weather patterns, I think?
Yeah. So,
and I just was curious if you could explain to me how it is that you know that that's a result of local weather patterns rather than something else, some flaw in the design.
my main explanation would be the fact that it did rain that night. I took note of that, and I actually presented this data this summer on the same premise, but also the sheer size of it. It doesn't really, reconcile with anything that I would have been looking for exactly in this kind of data. That's
So the size of the discrepancy
it's
is a sign that it had to be some other localized.
Especially in an area such as Boston. This is actually right out on the baseball field right behind the gym. There's not going to be an earthquake there. We have to be honest about that.
Yes,
so
no, it seems
we look for other explanations of some large data changes. Okay.
Great. And I did also, just to sort of return to kind of the initial premise, which is about earthquake detection. And I think you touched on this, but I'm a historian, so I'm slow to grasp these things. What is the link between the magnetic field? What do we understand about that link between the magnetic field, which I assume is why we care about using the magnetometer, and earthquake detection? What are we hoping to find there?
So a detail that I left out of this presentation, as it's not aimed to be as much more technical as my other ones, is the fact that when two tectonic plates either collide or pull apart, there is static electricity build up. I assume I'm buffering right now. My computer's telling me.
You're doing okay.
Okay, I apologize. And where these magnetic fields come from is the fact that in the rocks, the pressure creates a current. And where you have any sort of current, you have some sort of electric field. And where you have any sort of electric field, you have a magnetic field. it's a very material, physical property that comes from just the physical natural phenomena that happen with earthquakes. And we can see that there's a whole lot of precursors, we like to call them, between the chemistry of the water due to the electricity, the electrical current, I should say. There is pH of the water. There is all the way things floating all the way up to the atmosphere, which was actually Billy's thesis for the total electron content. So the electricity actually creates hydroxyls, I believe they're called. This isn't my area of expertise, but they created electron ions that floated all the way up into the atmosphere, the ionosphere to be specific, and create electron clouds. And this can be monitored as another sort of precursor. So really there is just an entire network of signals, precursors, we like to call, that we're trying to observe and that not a lot of people are looking at, which lends Eastern Asbury College as one of the leading universities in the field.
All right. Great.
If that answers your question.
I think it does. Yeah.
All right.
Within the, within the limits of my ability to understand such things, which are
I think
quite
pretty
quite severe. But yeah, Dylan and Jose and Liz, thank you all very much for sharing with us this evening and opening up these fields of inquiry. I'm always incredibly impressed by the work that you guys do and by what comes out of our natural science programs. So thank all of you for your contributions. Thanks to those of you who've been attending this evening. Just a reminder that you can find on the Symposium Canvas site, you can find many of these presentations if you want to go back, and discussion boards where you can be contributing questions to various participants and presenters. So there are lots of opportunities to follow up with these students and the other presenters that we have. So thanks everybody, and have yourselves a great night. We will see you back here bright and early, 8:30 tomorrow morning. So have a good night, everybody.